Today, in this lecture, I am going to explain a small topic. Actually, in the last session, we have discussed about three kinds of particles. There are three kinds of particles, and the particles which are obeying the Maxwell-Boltzmann distribution law, and some particles are obeying Fermi-Dirac distribution law, some are obeying Bose-Einstein distribution law. So, before going to a detailed study of Maxwell-Boltzmann distribution law, I have given some basic concepts on the statistical mechanics. So, just look here. Suppose we have a n quantum type particles. So, these are maybe distinguishable. So, the particles, suppose I have a total number of particles, n particle I have, and arranged in k compartment. I have k compartment. I need to arrange this n particle in k compartment. I need to put n1 number of particle in first compartment, n2 number of particle in second compartment, and n3 number of particle in third compartment, and so on, nk number of particle in k compartment. So also in first compartment, suppose I have different states. In first compartment I have g1 number of state, quantum state, and second compartment I have g2 number of quantum state, and so on. In that way, I can tell in ith state I have gi number of quantum state. So also we consider gi number of quantum states available in ith compartment. And if I have g1 or g2 and so on, number of states are there, I have n1 number of particle I can arrange in g1 number of state. Same way, n2 number of particle in different way, in different manner I can arrange in g2 number of quantum state. In that way, the different configuration, the way of arrangement in each compartment is gi raised to n. So this much number of different way of arrangement in each compartment. So in that way, so suppose I have this distribution for the number of particles, and what is the total number of distribution, total way of distribution. So I could denote as a W. So W is equal to n factorial, total number of particles, n factorial by n1 factorial into n2 factorial, etc. nk factorial. And each n1 factorial have different way of arrangement, g1 raised to n1, g2 raised to n2, and so on, gk raised to nk. And here the total number of W is, I can represent this by n factorial, and this is the product, or the product of, I put as a big pi, I raised 1 from 2k, gi raised to ni, and ni raised to ni factorial. So this is the total number of arrangement if I have k cell with gi number of states and total n particle. So this is what you want to know about it. This is the one thing. What is the use of this one? I will explain, and while doing the Maxwell-Boltzmann distribution law, we need to derive the Maxwell-Boltzmann distribution here. You need to find this equation. So please remember this one. And the next main point I need to add to in this lecture is, so we have there are different possibilities are there, because we have a macro state and different types of micro states. So the system can occupy or system can access any one of the states. So in that way, the system can stay in the most probable state of system is that the most probable state of a system is that macro state which has a maximum probability. Which is the most probable? It has a maximum probability. So the most probable state is known as the equilibrium state in statistical mechanics. So we have a different possibility in which one system, suppose one state has a maximum probability, such state is known as equilibrium state of that system. So very important point in this that. And the second point I need to add here, according to statistical mechanics, if two systems are in thermal contact, it may be in equilibrium later. So according to statistical mechanics, if two systems is in thermal contact, it will be in equilibrium if the quantity, which quantity? Dou by dou E. Dou means partial derivative of log omega. What is log W? So W is nothing but the total number of way of distribution. It's nothing but this maybe is a micro state. So log W by dou E, partial derivative of log W with respect to E is constant. Suppose I have a system here and I have another system here. If the fact it is in statistical equilibrium means dou by dou E of log omega W of this system is equal to dou by dou E of log W of this system. So this quantity should be equal. I denote this quantity as a beta. I denote as a new parameter here, E beta. So, but in thermodynamically we know if two systems is in thermal contact, it may be in equilibrium when the temperature of first system is equal to temperature of the second system. So, statistically this is the case, and in thermodynamically this is the case. So, from this one beta and T having a relation, from this one we can easily write this equation. The beta has a 1 by kT. There is a connection between beta and temperature. So 1 by kT, where k is a Boltzmann constant. And another very important point. So actually here we are dealing with the statistical mechanics, but we in the macroscopically we know only the thermodynamic properties. So you know in the old physics we have a fantastic equations are available. So in with some equations in the nature there is a lot of equations are there. E is equal to mc square is very famous equation, and Einstein gravity equations are there. And the same way there is some relations are there. How these relations came we don't know. They cannot derive it. They just taken from their mind thought or something. So some people told this is a God equation. Why the God while creating the universe maybe it's some thought only. So the God equation, because the equation coming from somewhere. So in that way there is a very famous equation. It's called Boltzmann entropy relation. You want to study this one. So it's very easily you can understand from this point. So I can explain here from thermodynamic system which is an equilibrium. So a thermodynamic system which is in equilibrium has a maximum entropy. So in thermodynamic point of view we know principle of increase in entropy and all principles, because it's telling that if a system is going on irreversible state, entropy is always increasing. Entropy is never going to decrease. So it means the system is reached at equilibrium, its state as a maximum entropy. So those in the last semester we have studied in the thermodynamics that system which is in equilibrium, it should be have a maximum entropy. This is the point thermodynamic point of view. This is what is this point. From thermodynamics, system which is equilibrium has a maximum entropy. So the same way, what is the point from the statistical point of view? From the statistical mechanics, system which is equilibrium has a maximum probability. The maximum probability has the system, the state which has maximum probability is known as which is equilibrium state. The same way from statistical mechanics, system which is equilibrium has a maximum probability. So this is 2 points. One is in stat, one is thermodynamics. What Boltzmann did? Boltzmann connected these two. He's got an idea. Yeah, in the thermodynamics, one system has a maximum entropy. The equilibrium means it has a maximum entropy. And in statistical mechanics, the system has an equilibrium means the state has equilibrium means which has a maximum probability. So Boltzmann think that then there should be a connection between entropy and probability. He tried to connect this equation. So that kind of equation is called Boltzmann entropy relation. In 1896, he found this connection. One is a macroscopic point of view, and another one is a microscopic point of view of arrangement. So there is a connection between macroscopic and microscopic. There is a connection between thermodynamics and statistical mechanics. Here entropy is thermodynamics and probability in statistical mechanics. So this connection. So that's why I called it a bridging connection. There is bridging connection between thermodynamics and stat mechanics. So this is the thermodynamic relation. That is T is equal to dou E by dou S. So from that one thermodynamic, you can find this relation. 1 by T is equal to dou S by dou E. And but we from this one from this one 1 by T is equal to K beta. So this equation from thermodynamics 1 by T is equal to dou S by dou E. So from this equation 1 by T is nothing but K beta. I just substitute K beta. What is beta? From this statistical mechanics, from beta is nothing but dou by dou E of log W. So K into dou by dou E of log W. So there is a dou S by dou E. So dou S by dou E is equal to K into dou by dou E of log W. So what is this one? Both are dou by dou E. Here also dou by dou E. So K is a constant, I can take out inside. So what is S? S is equal to K log W or log omega. Somebody called omega also, so no problem. What is omega? Is a independent way of arrangement of particles, so it's nothing but microstate. So S is equal to K log omega. This is a very famous equation and very important in the stat mechanics, because the left hand side S will give the entropy. Entropy is a parameter in the microscopic point of view. It's a thermodynamic parameter. W or omega is nothing but it's a microscopic arrangement of particles. So once we know the microscopic way of arrangement, that is the number of microstates we know, we can find the entropy, and once we know the entropy, we can find all other parameters. So once from the microscopic, we can, once we know the W of the system, we can find all other thermodynamic parameters once we know this equation. So this relation is called Boltzmann's entropy relation, where K is called Boltzmann constant. This is a very famous equation. Such equation is called bridging equation. So you want to know this much point. I will explain in the next lecture how we can derive the Maxwell-Boltzmann distribution law. In the later class, I will go to the next distribution law. So before that, you should go through this point and you may get a good clarity. Then we will derive the Maxwell-Boltzmann distribution law. I think it is okay. Thank you.